I'm going to continue a bit on the previous presentation from Roland and Colin and dive a bit into the optimizing compiler. So this is a bit concrete. So we're going to go through compilation and talk about more ARM-related issues. So So we're just going to quickly go over the compilation process overview for those who didn't attend the previous presentation. Then we'll look at the compiler from the point of view of a developer to see how we run some code, we analyze it, and how we optimize the compiler. And then we'll discuss some issues about the compiler and development. So again, this is the compilation process. So we start on the left with some Java files that we compile to some text bytecode that's been inherited from previous versions of ART. And then we start the compilation process. And we have our optimizing compiler that's run by the dex208 executable that transforms this text bytecode into a graph composed of blocks, and every block is composed of instructions. So instructions are things like add, sub, return, go to. So they are rather simple and named after what they do. For those who are not familiar with compilers, the basic block just contains a series of instructions, and they're always executed from top to bottom. And we cannot exit from the middle of a basic block, and we do not enter in a basic block. So we'll see a bit more later. And here we have the graph. Once we build the graph, we're going to run a series of optimizations on it. So we talked about it earlier, and we're going to see a bit more of the details. The optimizations will transform the graph, and eventually we go to code generation, and we translate every instruction to some assembly. So an hadd is going to be translated to an add, and so on. And on the right, we have an output file that's like an elf file that contains the assembly. So some of the instructions run. So we talked about them before. You should be familiar with them: inlining code, dead code elimination, strength reduction. So that's, for example, applying arithmetic identities. So if in your graphs you see variable multiplied by 1, you just replace that with variable to avoid useless multiplication. Okay, so the first thing we do, we have, let's say, some Java code, and we want to run it with this compiler. So we download the AOSP code, we compile everything, then we use the Java compiler. We compile the Java code, we push some things on target, and we run it. So the commands are going to appear here. They are here for reference in the deck, in case some people want to go over it next when they are home. It doesn't matter right now. It's just there for reference. All right, so here are some comments, and we continue. Now, when I'm trying to analyze the compiler, understand the compiler, I don't always want to run on target. So actually, I'm often cross-compiling. And as mentioned previously, we use some debug information. So again, here there's a command. Again, we do not care about the full command. We only care about the red part. So the executable called dex208, we see that we generate some code for ARM64. And at the very end, we give some instruction to the compiler to dump debug information. The -j one is just there because otherwise the compiler would use multiple threads, and it doesn't support dumping the debug informations with multiple threads. So this produces a text format file that contains the state of the graph before and after every pass on the graph. It also includes some disassembly of the generated code, so it's very convenient to see what code we produce. With a bit of experience, it can be read manually and understood, but otherwise there are some tools that have been mentioned, and you have the links here that can build you a nice graph, and you have easy access to the information. Now, for the rest of the presentation, we're going to use a code sample. So this is a code sample inspired by real code. Of course, it had to be simplified because, as you will see, it's hard to fit everything on the slides, so it's very much simplified. So the idea is to do RGB compression. So our original data is an array of 32 bits value, so integers, with 3 8-bit channels, red, green, and blue. And our target in this example is to reduce that to use only 16 bits. So the idea in real-world use cases is that we want to maybe fit two 16 bits, so two pixels, into one 32-bit value. So we just take the input. We take only some bits of the top bits of the value, and we shift it down, we mask it, and we shift it down. So this is a lossy compression, of course, right? So we just keep the top bits, and the bottom bits of every channel are discarded. And this is the Java code we use to do that. We declare some constants, and then we have a loop that iterates through the array. For red, we shift down the bits for red, and we mask it. We do the same for green, the same for blue. We OR everything into the result, and we store that back into the array. So I'll just leave a little bit of time for those who follow the code to have an idea. So we do the same thing for the 3 colors. Now, stick with me for a few minutes. So this is the hard part of the presentation. So we're going to look at the internals and what the internal representation of the compiler looks like. So on this first slide, there will be quite a lot of stuff at the beginning, and then everything will become much simpler as we go through the compilation process. So now we are building the graph from the DexPyte code. So the first block in the graph is the function entry. This block contains some instructions, and then goes to another block that only contains a goto. Then the control flow continues to a loop header. So this is the real representation of the graph that's built by the compiler for the code example we saw before. Then the loop header goes to the loop body that executes. At the end of the loop body, we have a goto that goes back to the loop header, and we continue like this until in the loop we meet the exit condition, and we exit toward the end of our function with a return statement. Okay, so that's how the graph, the blocks in the graph look like. Now, that's how the instructions in the block look like. So in the function entry, we have an instruction that represents the input parameter. So here, in this case, it's the class object. It's just the object on which the function calls, the equivalent to the this pointer in C++, for example. It also declares some constants that are used in other places in other blocks. So we still have this almost empty block with a goto. We'll see about it later, where it's there and where we keep it. And then we have the loop header. So I put some colors, I don't know how much you can see, to try to show. So the IRs are named after what they do. So the null check checks that pointer or reference is not null. An array length retrieves the length of the array from the array pointer, the array reference. And we have greater than or equal comparison. So on the left, we have a column that gives the identifiers of the IRs. So the numbers are just index that are allocated increasingly as the instructions are created when we build the graph. They don't mean anything. They just identify every instruction. The prefix letter indicates the type of the IR. So if we look at the array length, for example, it represents I17 in red in the middle here. And it indicates that the array length is an integer. And we see that this I17 is used in the comparison greater than or equal just below. So here in the loop header, if we go a bit through it, so we have the parameter value that's checked as being, so we check it's not null. If it's null, we're going to throw an exception. That gives us the result, which is the same pointer if it's not null. From that, we retrieve the array. We check that the array is not null. We retrieve the length of the array. We compare it against the induction variable, so the I in the array I. And depending on the result of this comparison, we either branch to the loop body or we exit the function. Okay, so I just leave a bit of time to look at that. So we are in SSA form here. So if you don't know what that means, you don't care. You will still understand the presentation. For those who know what that means, we stay in SSA form for all the optimization passes in the compiler. Okay. Now this is what's inside the loop body. So I divided this into 3 blocks. So the first part is what we do for the red code. So this is the hard part, then it gets simpler. So on the left, we have the IRs, the internal representation. On the right, we have in blue the Java code, and then some comments about what's happening in the IRs. So if we start from the beginning, for the color red, first we check that the this pointer, so the object pointer, is not null. Then we retrieve the array. That's the second line. Again, we check that the array is not null, and we retrieve the length of the array. Then we check that we are not accessing past the length of the array. That's the bounce check. Finally, after all these checks are done, we retrieve the value of array at position I. We shift the bits down, and we mask it. We do the exact same thing for green and for blue, just with different values for the constants, for the masks and the shift. And then at the end, we OR all the results, and we store it back. So again, we check that this pointer is not null. We retrieve the array. After that interleaved is the ORing of the intermediate values. We check that the array is not null. We retrieve the length of the array. We check that we are not storing past the end of the array with this bounce check. And finally, we perform the store. So this is a lot of things, and as you could see, I had to fold the code for green and blue. So let's not try to see all the details now. One thing I forgot to mention, sorry, is that, so in the IR column, the first column with the numbers and the prefix indicate the ID, and of course on the right, in between the brackets, these are the inputs to the IR. So if we look at the bottom of the first block where we have the shift and the end, we can see that the result of the shift is I39 and is used into the end just below. And I41 refers to a constant that's been moved away in the entry block. So now we're going to go through 2 optimization passes and see a bit how they work. So I've come back to the general structure for our graph. And on the right, I've expanded the code for red and for green, and the code for blue is still folded. Note that it's not the first optimization pass. So actually, some instructions have already been removed. In particular, the null checks. Some null checks in the loop body have been removed. But we'll see on that. So the GVN pass, the global value numbering, will be used and will be able to remove some IR. So here, it notices that all these instructions in orange, they actually perform the same thing. So these are the same instructions on the same inputs, or equivalent inputs. So for example, if you look at the instance field get, that's the first one of all these orange blocks, it always gets the array value from this pointer. And so the GVN is able to recognize that and replace, so delete the instructions that are just a repeat of what's been done in previous. And update to use the first time we do that. So instead of doing it multiple times, we just keep only the first time we execute those instructions. And where previously an instruction that was deleted was used, we replaced by the first one. So that was a series of instructions. So after we delete them, we get there, so we simplify. Now we can extend the code for blue, where the same optimization occurred. And again, we see that when we access the array, we do a bounce check every time we retrieve the length of the array. No, that was before. We do a bounce check and we retrieve the value of the array every time. So same, we only do that once, and we reuse the first one. So after we've deleted all that already, our code has been simplified a lot. Now we go to next optimization, that's loop invariant code motion. So here the idea, if we remember, is that if we retrace back the code, so we are in the loop header, we go to the loop body, at the end we go to the goto, we go back to the loop header, executes all this, and so on. And we can notice that actually all the instructions in orange here, they don't depend on the loop. This is doing a null check on the array to verify that the array is not null. And the array doesn't change within the loop. I mean, the reference to the array doesn't change. So the loop invariant code motion pass finds that out, also finds that the array length, and arrays are immutable in, the array length is immutable in Java. So all this can be moved to this little block that was useless before, but that we can use now to move these instructions up. And that's what we get at the end. So, so we couldn't count at the beginning, but we've gone from more than 30 IRs in the loop body to a dozen, I believe. 1, 2, 3, 4, 5, 6, yeah, so 13, I think. And in total for the loop, it's also many fewer IRs. So now we've just seen, so that was just to illustrate a bit how an optimization pass works. Now we have our code sample, so that's our RGB compression, and it's still running too slowly on our device. And of course, that's a representative piece of code, and we want it to run much faster. So how do we make it run faster? So one way to, of course, rewrite the Java code, but we are not the people writing the Java code. We only work on the compiler. We are not controlling the source code. So we're going to try to optimize the compiler. So first thing is to try to profile the code and see if there are any hotspots that we can optimize. Another thing we can look at is look at the compiler upstream and see if there are optimizations available for other architectures that are not yet implemented for ARM or ARM64 and that we could port and that would be applicable in this example. And sometimes we don't find any hotspots either, but you can notice by looking at the code that some code patterns are very frequent. So although you don't see a hotspot, the same code patterns happens many times and is suboptimal. So we could also try to optimize that, for example. Then once we find some ideas of what to do, we want to have an idea of whether it's worth doing. And so we want to evaluate optimization. So we want to try to think about the impact on performance, on code size, and on compilation time. There's a word missing here. We want to try to think how many times the optimization will be applicable. And a personal method I like is reverse optimization. So sometimes implementing an optimization is hard, right? You have to do a lot of work before you see how it works and maybe try to find what the benefits can be. Another idea is to actually do the opposite. So when you know that the code patterns could be optimized, instead of optimizing it, make it worse. So add some knobs or maybe duplicate the code and see what the impact is on runtime. So if you had a code pattern that was run many times, you insert 3 knobs there. If there were 3 instructions, for example, you rerun that. And if you get 50% performance hit, then you know that optimizing that could be interesting. And then we want to implement something. So the better way to go at that is to have a look at the patches upstream. So as was told before, all the development happens upstream, and the code is rather clean. So let's profile our code example. So the good news, we have Linux perf in Android upstream, so we don't need to do much. There is an additional slide in the deck at the end that gives all the commands and some example on how to do that with symbols for the Java files and everything. But the commands don't really matter now. We don't want to look at that. And we just use it the standard way. We use perf. So we just do perf record with the standard commands, so maybe Java and the benchmark. And then we use the report command to show the results. There are some other tools that can be used for profiling that can be useful. So Streamline is one. One of the interesting features of Streamline is to show a graph over time. So you can see samples over time. So if you have an application that runs for a long time, for example, you could distinguish different phases and focus on a specific one. So we profile our representative code sample. And oh surprise, we spend almost 70% of our time in the compression function that we wrote. And if we dig in, oh surprise again, we spend most of the time in the loop. So that's the code generated for the loop. So we can see at the top the initialization of the counter, the loop exit comparison and branch out, and then we load the value from the array, then we have the shifts and the masking, and at the end we OR and we store back in the array. So now we are trying to optimize the code generated. So what do we want to do? So I'm sure some of you will have spotted already. We're doing binary operations with a shift, and on ARM we know we can actually encode that into one instruction. So that's something we want to optimize. That's very common for ARM, of course. Another one that's a bit less obvious to see here is that we have two instructions here that are duplicated. So here, this is before the array get and the array set. So before we retrieve the value from the array and before we store the result back. So the reason is that in Java, it's not like in C where your array is just a pointer to the beginning of your data. There's actually a bit of metadata before the values start in memory. So to do the get, we actually have to take the reference, add this offset that goes past the metadata, and then load the value. But we're doing that for every array access. So next now I've put the IR, so that's the IR, and that generates this code. So we see that for most IRs we generate only one instruction, but not necessarily. So now we want to do our optimization. So the first one is how do we represent our AND and shift operation into one IR, right? Because when we are going to generate the code, we need something to tell us that. And this is not something that's useful for other architectures. So how do we represent it when the compiler currently, all the IRs are architecture independent? The other one is these array accesses in orange. Is one IR generated two instructions. So all our optimization passes, they operate on the IRs, not on the generated assembly. So how can we share this add instruction, assembly instruction, when they are generated as part of the IR? And do we do this everywhere? For example, Intel only generates one instruction for the array accesses because they have some more complicated memory addressing modes. So in many compilers, the solution is to have another level of IR, so a lower level of IR that represents something new. So here, we do that. So that was discussed before, actually. But the process, oh, what's happening? Yep. So what was decided, so we implemented that at ARM, as Linaro assignees and discussed with Google. We do need architecture-specific IRs because we want to represent things like this add and shift, so merge binary operations. But we're going to do it at the same level of IR. Why? We're not a huge compiler. We're not doing a huge amount of work. And right now, we go from this, at the end of the compilation process, we go directly from the IR to code generation. So instead of lowering all the graph and translating all the graph to this new level of IR, potentially losing some information about what's there, and then not doing much work with that anyway, we just selectively lower the IRs that we need to. So there's no point translating the add. So we started from Java, from the plus sign, that has become a DEX add bytecode, that has become this H add instruction. Eventually it's going to be an assembly instruction. Do we really need another level saying that this is a lower level add? I mean, we haven't gained anything there. So instead, we're just going to do selectively. So anything that's too high level and where we want to split it into something more expressive or something that's more adapted to the architecture, we split. The rest, we don't touch. Also, that allows us to reuse existing optimization passes. We don't have to re-implement other passes. So I'm looking in particular at global value numbering or loop invariant code motion, and we'll see an example just after. And so the framework we put in place to do architecture-specific optimizations, actually it's almost nothing. It's just the possibility to add new IRs that are potentially reserved for one architecture. So we prefix them with the architecture. And we just add an optimization pass, a compilation pass, somewhere in the pipeline to translate architectures independent IRs into architecture-specific IRs where we need. So in our case, for the array, what we do is we simply split it. So where we had a get before, we say, okay, actually an array access on ARM is first computing this intermediate address and then retrieving the value from this intermediate address. So we introduce a new pass that just does this, just this. It just splits the IR in two, nothing else. At this point, if we just generate the code now, we're going to generate exactly the same thing as before. We don't gain anything. But the splitting of the IR is very easy in the compiler. We just go through the instructions. Every time we see an array access, we say, oh, wait, just insert this intermediate address computation before and use it. But what we do is we just rerun the GVN pass. So that was already implemented by Google. I didn't have anything to do. I just copy-paste, rerun that after my pass. And suddenly, the compiler notices that the computation of the intermediate address is the same for any array access that we have there, and shares them and update them. So suddenly, we will have only one time a computation of the intermediate address. Using the shifter operand, we just add this long name IR that represents a data processing instruction that can use the shifter operand. And in the same pass, when we see a binary operation that has a shift or something similar as an input, we just merge them. So we delete the two instructions here. For every shift and AND, we delete them, and instead we insert something that reuses the input. So in the example, the input is very simple. So the IR, we have a shift, an AND, a shift, an AND, a shift, an AND. In reality, we are able to do this transformation in much more complicated cases. So we are able to do that if we have multiple uses for the shift. We can decide that maybe if there are multiple uses and they cannot be optimized in all cases, we are not going to merge it. We can do these kind of things. We can do the optimization across basic block as well, because we are operating at the HR level, so we still have information about that. And that's the code generated at the end, which is not bad. So that's for the loop body. So we've shared the initial add instruction for the array access. We have 3 binaries, so the ANDs with the shift node inside, and we store back the result. We're not going to discuss at the end. We have the goto that jumps back to the beginning of the loop, and the extra instructions are to do with some Java semantics and synchronizations. So that's not bad. So I'm just going to go back 1 second. So now what I want to do is to benchmark the results of doing our optimizations. So the idea here is that the code sample I've used is a representative benchmark or some representative code that's used in real world, and I've run it. So these are relative numbers. A53 and A57 are on different tables because on the platform I was using a Juno. They were running at different frequencies when I benchmarked, so it makes no sense to compare them when they were running at different frequencies. And we see that, so if we add the array splitting on this benchmark, we gain about 10%, a bit less. And if we add the shifter operand use, we go to 27% on Cortex X53 and A57. So yes, that's results on a very targeted benchmark that was put together specifically to illustrate these optimizations, right? So the result on real benchmarks obviously is not the same. At the same time, I didn't go as much as possible. If you try to cheat, well, not cheat, but if you implement a really targeted benchmark, you can go to 100% performance improvement easily because you just high latencies and you have fewer instructions. So the patches right now are in review. So most of this framework has already been merged into top of tree. There is one last comment to address. So the array split patch has been +2 multiple times by Google, but after it's been rebased, now there's a minor comment to address, and I haven't had time to push it while I was preparing the presentation. And the shifter operand is already for review as well, so you can have a look. And it's really rather simple to implement these optimizations. once we have evaluated our optimizations, we want to upstream them. So before we do that, we don't forget to add tests, a lot of tests. So the testing infrastructure in the optimizing compiler I find is really good, including this possibility to use the apply tests on the intermediate representation. So instead of just checking a before and after, we're actually able to peek and confirm what transformations are applied at a very specific place in the compilation process. That's really useful. And then everything happens upstream. So our patches first go through Linaro's Gerrit. So for Linaro members, you should be able to have access and look at them. And once we've approved them internally, then we upload them to the Android Gerrit. And if you want to contribute, which you are more than welcome to, especially if you want to implement some architecture-specific optimizations, there are some instructions on Linaro's wiki and, of course, the Android documentation. So now I'm just going to discuss quickly about some topics. So here we just showed how the optimization passes work, and we said, oh, the compiler sees that we can share those instructions because they're the same. So we delete those and we replace by those. So doing the transformation is actually relatively easy. You have a helper, you take your instruction, you say, delete this one, add one here. What's really hard, of course, is to actually recognize what you can do in the compiler, right? So find what can be done and make sure that it's correct. The compiler has been stressed by the Google presentation before, but I found, so from an external point of view, that it was easy to extend. So the compilation passes are really clean and easy to work with. And another example is that we use Vixel. So there will be a presentation at the end of the week. So it's an assembler, disassembler, simulator for ARM64. And there is the 32-bit port as well coming that's been written by ARM. And this is the code that also went into the Google V8 just-in-time compiler. And we've actually been able to use this instead of the ARM64 assembler that was already there for the previous compilers. And Vixel provides some additional functionalities that are really useful. And Google was very helpful to integrate it, although that meant in some places a bit of tweaking of the code because the internal representations for some structures are different compared to their assembler. Things I wish I didn't forget is the compilation time. So I have to be careful about that. So when we do the optimizations, we tend to look at the generated code and try to do something beautiful. But of course, we have to remember that we cannot throw some very time-consuming optimization for little benefit. Today, there are many architectures supported in the optimizing compiler. So until today, almost all the compilation process is architecture independent, up to register allocation and code generation. And so now that's changing with the introduction of architecture-specific optimizations. And for now, there are, I believe, the first architecture-specific optimizations that are going to land are going to be for ARM64. And for Intel are following. They're also looking at it. But there's no, well, there are probably some patches for review. I'm not sure. So the fact that the compilation process is architecture independent up to late in the process, it hasn't been an issue until now, but it theoretically could be. So we can discuss these ideas a bit more in detail. So one dream I had was to have condition flag consumption production as a side effect, but this would prove a bit hard because it doesn't match what other architectures would do, for example, MIPS. Issues with development. So, can somebody please give me a stable platform for development? So, non-Nexus devices. So I work with the Juno, for example. I try to work with the High keyboard. So I try to do this presentation with the High keyboard. And the wiki, the tutorial worked fine, and then some things weren't working, and I was talking with the maintainer of the High keyboard, going with him through the steps to try to flash an AOSP top-of-tree system image on my device. And it wasn't working because there was a bug in the firmware. So it's difficult sometimes to work with non-Nexus devices. The Nexus devices have the advantage that they are well supported upstream because Google makes sure that they always work. Although I've used the High keyboard and the Juno quite a lot as well. Even on Nexus devices, we have to be careful of some things. So be careful about frequency scaling, and anything that can affect performance that's not into the compiler. So if your screen is off or if your screen is on with the default AOSP image, it influences the frequency at which your CPU runs. So you want to be careful about those things. In optimizations, we have to be careful about different behaviors on different CPUs. So we have CPUs coming from a lot of partners that have different behaviors for different instruction sequences. So ideally, we don't want to over-optimize for one specific CPU, just because there's no point, because what's really good for one CPU may be a bit different. In practice, I've made this case for recent optimization where on one device, the optimization was faster, but it was slower for another one. And in this case, it's a bit hard to know what to do. In this particular case, it was easy because the following patches in the series actually improved things for everybody, but locally, it made things worse for one CPU. Benchmarks. So why do I have to use the GUI to run some quadrant or lean back or benchmarks like that? So I'd like to have good benchmarks, if possible, that I can run on the command line without having to take my mouse, please. We are working on that. We have a repo that's public in Linaro now, where we are introducing a series of benchmarks, and you're welcome to join and help us. Right now, the work is to port some existing benchmarks to use, and I think we can talk with Scott, that's over there in the room, if you have some questions. And finally, working with Android is not always great, but compilation is not too slow if you have a 20-core machine with a hyper-threading. So what we are working now, so the Linaro art team, we're working on quite a few things. So the benchmarks, I was just saying, and we are working in the room just next door. Working on more instruction simplifications and ARM-specific optimization, so that includes things like conditional select, conditional set, and many more. We have also started some work on instruction scheduling, so some instruction scheduling has been done in Quick, so some people must have access to those patches. So we started that in optimizing as well. So the slow path sharing, so this is some code size improvement patches mostly. I mean, first code size, and we hope maybe it will also yield some performance improvements. There's also some work on intrinsics and on the simulator. So the idea of the simulator is to be able to run the compiler tests, only the tests. Like we're not talking about a full CPU simulator. To run the tests on hosts, because it makes it easier for debugging and tracing and all these things. So there's a lot more to do, but the framework and the project is in a good shape. So for ARM in particular, we have now a lot of work to add ARM-specific optimizations. So you're welcome to join. Any questions?
So are you planning to do anything for Neon? Neon 64 stuff?
So we all dream about Neon, and we all dream about implementing some beautiful SIMD optimized stuff. This is not the priority, right? We have a lot of things to do.
Why not is the priority then? Neon 64 is powerful.
Yeah, but today, I mean, it would require a lot of work when we see the state of parallelization in other compilers that are much more advanced. We have a lot to do before we get to that point. First, code generation we can do. VXL can generate Neon code, so today you can go and generate some Neon code if you want, but we don't have the infrastructure that sets the code in place and the compilation path that gets everything in shape for producing good Neon code. So,
Same as GCC, the intrinsic stuff doesn't have.
yeah. Stuart?
So ARC's not structured yet for...
Yeah. Wait, sorry, maybe microphones.
So that would be a... I'm a bit of pessimistic, you know. We got 64-bit crazy machines, and then we're running on certain things. It's not optimized for 64-bit. I think from this year onward, most of the mobile phones 64-bit. Yeah, we should get the Leon working properly to take advantage of all the super duper instructions.
So the optimizing compiler is still being developed.
Yeah.
So there's basic things that are still being done there. So like from previous presentation, it's not, till very recently, wasn't handling try and catch blocks.
Yeah.
You're going to handle try and catch blocks before you start doing neon. The register allocation just now is being improved. It can deal with that now, but there's nothing yet for any vectors, for any SIMD in any architecture yet. So there's a lot of groundwork to be done before you can start considering that.
Just to remind you, in previous presentation, you were told that the compiler is 1.5 years old, so it's really the beginning of the compiler. There's a lot of infrastructure that's needed before we can get there, and many more things that will probably bring, relative to the costs, better cost to performance improvement, or rather performance improvement to cost benefits before Neon.
But we are aware of it. It is something that's under consideration. It's a case of how we actually allocate a resource.
Yeah, that's why I'm saying that you guys' priorities based on whatever numbers you guys saying now Neon will be 64 will be lower priority.
Yeah, I mean, if you make something 4 times quicker in about 0.1% of the cases, it's less compelling. It really depends on what most code is executing.
Yeah. So we see. I will push a bit the LMG to do it because one of the problem is I think is now we have a lot of image processing is done in the DSP, and some of the crazy app is using Java to do it, and we see some funny things. So we push them. Okay, we ask the app say don't do your image processing on the Java side. We do a Neon assembly library for you. So we find it. Oh my God, image processing stuff is if you're using Neon 64, it's much more faster than.
Yeah, but here we're talking about like compiling all apps from the.
Yeah, but you think about it, right? A mobile phone.
Sorry?
And you think about a mobile phone and camera, image processing is 50%.
Yeah, why is?
I have no idea. This is the app. This is the app.
Put it this way: in Java, an array, a two-dimensional array, doesn't have to be square. It could be triangular. It could be.
Yes,
round.
that's why I say, right. I find it strange, but there's million developers out in the world doing image processing in Java, and I tell them no too, but.
There's limitations on the optimizations you can actually do in Java when you're doing SIMD over arrays. There are things that can be done. There's some certain hard limits that limit what's possible, and for that kind of thing, you'd be looking at API or language changes. So you may be able to get a little bit far, but there are set limits on what you can actually do compared to, say, assembler and running Neon.
Yeah.
So auto-vectorization is a hard problem.
Yeah,
and in Java it's even harder.
I think even in C it's hard.
It is.
Yeah.
And there's more scope for what you can do there.
Yeah. All right. So
We can talk about it more in details outside.
Yep. Yep.
Any other topics, questions? No? We're done. Okay. Then thanks for coming.
Thank you.